I'm Appie Sluis. We scientists use sediments from the ocean floor to reconstruct the climate history of the Earth. But how do we get those sediments? That's a completely different cup of tea. And I don't even like tea. I like my hot espresso in the morning. The work that's done here by the drillers is hard physical labor and stands in sharp contrast with the microscope work that's being done by the scientists in the paleo labs. How does the drilling really work? There are 20 people working day and night to recover these sediments from the ocean floor by hard labor. Let's try and get a little bit of a better insight in the drilling operations that are taking place here on the JOIDES Resolution.
This is PNN.
This is a real deep water drill ship, so we have a lot of heavy tools and high weights that we operate with. The derrick is 193 feet off the water line, and it's just rated for 1.2 million pounds. Aft of there, you'll see the big long skate area. That's where our pipe racker is. This ship is quite different than most modern drill ships in that we have a horizontal pipe racker. Most new ships have vertical rackers for all of their pipe. One of the reasons we do it this way is it's very efficient and very fast. We can trip pipe nominally 25 stands per hour. Once we get down to the sea floor, we rotate the top drive into the center and hang it off of the bales. That's what this yellow piece of equipment here is. What the top drive does is it rotates the pipe. It provides the drilling RPM and torque that's required to actually rotate the bit and cut the core. That's the iron roughneck, that big piece of red equipment there. The iron roughneck comes out on these tracks and is used to screw the joints of pipe or the drill collars together. It's very important that our connections are made up to exactly the right makeup torque. If they're not made up to the right torque, that connection can start to flex. It leads to a crack and ultimately a failure in the connection, and you lose a large portion of your drill string. And because our drill strings are typically $1.5 million a piece, we don't like to lose drill pipe we do everything we can to avoid that. When you're operating with this much weight, you have to be able to stop it. It's one thing to be able to lift it, but when you've got 700,000 pounds being lowered down toward the rig floor, you better be able to stop it when you get to the bottom, or it's a pretty bad train wreck. So we have multiple braking systems to be sure that no matter what happens, the driller can stop everything when it gets to the rig floor.
I'm Craig, I'm the driller. Canadian. I've been on this rig for maybe 12 or 13 years now. The most important part of this job is I would say the safety of the crew. The second responsibility on this vessel is to assure that the drilling equipment is in operating condition. Third, and probably most important to the operation, is to get the core for scientists. It's a good job with responsibilities. It's a good job with working with people from all over the world.
Before we start drilling, we have to have what's called a bottom hole assembly. That is the drill collars and the outer core barrel equipment and the bit, everything that's used on the end of the drill pipe that actually cuts the core and allows us to land our core barrels and recover the cores with our wireline coring system.
The bottom hole assembly usually consists of your bit. This is the weight of your drill string. All your weight is associated with your bottom hole assembly. It's like a pendulum. A string with a heavy nut on it. As long as you don't put any more weight than the BHA weighs, it's only going to go straight. Gravity does all the work.
So we always have all of our joints of drill pipe under tension. Then when you cross over to the bottom hole assembly, the drill collars allow some of the weight. What the driller does when he's drilling is he slacks off a little bit of his brake on his drawworks and takes some of the weight and applies it on the bit. We keep the neutral point somewhere in that bottom hole assembly. You never allow it to go up into the drill string, because that would mean that some of your drill string joints are then in compression, and that's not a good thing for us. Passive heave compensator that we use is this big yellow machine here hanging in the derrick. Has two big yellow cylinders going up.
The heave compensator is part of our traveling assembly, and it compensates for the vessel motion. So if your bit is on the seafloor, it cannot move. So all the motion and anything that is associated with the vessel moving up and down in waves is compensated by the compensator. We can operate in anything upwards of 30-foot seas comfortably. Anything after that's a little uncomfortable.
This Cortex shop has been on the ship since its beginning. It's a good full-service facility, as well as a maintenance shop, as well as a place to little solace from the outside environment to work on the equipment. We're coring in soft sediments. For these soft sediments, we're using the APC XEB coring assemblies. The upper portion of the APC actual core barrel assembly has two very definitive parts that are used hydraulically to actuate the core barrel to stroke it 9.5 meters out of the drill bit like a cookie cutter and cut the formation so we can retrieve the samples down below the drill bit. These assemblies are the inner shear pin and outer shear pin assemblies. They just function as an inside sliding sleeve mechanism with two shear pins. When this assembly here slides up on here, the outer shear pin slides into place. It's locked into place by two shear pins and the inner shear pin. So when it goes in here, the drill string is pressurized from the surface, the pins shear off, and the core barrel assembly strokes out 9.5 meters past the bit and retrieves the core. Once it's stroked out and we retrieve the core barrel assembly to the rig floor, we retrieve it to the floor, we take the coring assembly off, take the barrel out of the pipe, remove the liner from it, reload it, and as we're reloading it, we once again slide this assembly together, engage these shear pins into place, and that's what keeps the barrel intact while it's traveling down the drill string prior to being fired. At the lower end of the drill string, we have a drill bit. Drill bit's what cuts your material, cuts the formation, and the core barrels extend outside or work in conjunction with the drill bit. Okay, on the very bottom of our APC core barrel is our APC cutter shoe, or our cookie cutter shoe. As you can see from the interior, she has a very sharp profile, tapered but sharp profile to act in a knife formation, knife action. She slides in and slices into the core. When our sediments down below are not able to be penetrated by the APC, we'll switch over to an XEB coring assembly. The XEB works similarly just inside the very same pipe that's down below. And what we use on that is a drilling style system. On the lower end of the core barrel, we have XEB cutter shoes. This is a soft formation shoe. Just a little bit, this will cut a little bit firmer stuff than just this knife blade, but this works in a drill bit motion, so it cuts it as it turns just as the drill bit does. It works in cooperation, it turns just while the drill string does. We go from soft here to an even harder formation shoe here, as you can see from these tungsten carbide tips on here that are impregnated in here. This assembly for these shoes is a very unusual system because they're a cutoff, they're a throwaway from what the U.S. government uses, the Army uses on the U.S. M1 Abrams tank. They have, I believe it's a 105 millimeter barrel on there, and they cut the barrel off. They put it into place to a certain fixed distance, and they get whatever distance they want, and whatever their cutoff is, we as a government contractor, we buy those cutoff pieces and use them for the rest of the business. They use it for the warfare and we use it for the coring tool, so it's multitasking.